different reference books. First question, students, sir, do we need to read the reference books? Class, no need. We already extracted the very important information and board exam relevant topics here in our QRC manual. So mainly we use your McMurray, your Smith, your Wade, and Stoker organic chemistry and general chemistry. So somehow I also read Solomon's in order to enrich our discussions, particularly in our mechanisms of different organic reactions. Okay, so class, again, we are now going to start immediately with our crash course number 1. So please bring out your manuals, your annotators, your highlighters, or any paraphernalia you need for note taking. Because at this point, we will start with our introduction to biochemistry under your crash course 1. So for this video class, we will start discussing a brief history of your organic chemistry, how it was developed as a field of chemistry. Secondly, we will also discuss some examples of representations of organic compounds. So particularly, we will focus first on the two-dimensional representation. And lastly, we will also discuss the relevant properties of carbon that gives its chemical reactivity. Our class, here in your properties of carbon, of course, this is somehow related to your discussion in organic chemistry. Before we formally start our discussion, of course, I have a quick quest, okay? So here is our mini game for this topic. So here is a 4 picks 1 word type of mini game. As you can see, we have 4 different pictures and then identify the common theme here in our first item. Class, you can pause the video and I will carbon class like the organic or healthy. Okay, I will cover to hold this with of developing the important concepts of organic chemistry. So sir, do these topics appear in the board exam? Well, class, relatively no, but of course it's important that you know how OrChem was developed as a subject. So for our first scientist, so this is Justus Freyer von Liebig. So are you familiar with your Liebig condenser? Remember, it is termed or coined after Justus von Liebig. So in English pronunciation, we pronounce it as Liebig, but in German, we pronounce it as Liebig. Okay, so again, for your development, our key founder of OrChem, we have Justus von Liebig. Secondly, we have Michael Faraday. Third, we have the pioneer in discussing your structure of benzene, of course. He is August Kekulé, okay? So this pioneered your Wöhler synthesis. So he is Friedrich Wöhler. And second, we also have Edward Frankland. So they are simultaneously developing, or they simultaneously developed for your Wöhler synthesis. We have Friedrich Wöhler. For your organometallics, the synthesis of organometallics, we have Edward Frankland. And lastly, we have Archibald Scott Cooper. Our class, in your manual, we already provided the major contributions of each chemist here in our picture. So to summarize again, task, Justus von Liebig, he founders of organic chemistry, okay? So for Michael Faraday, so if you're familiar with Faraday constant, of course, we use it in our computations, particularly in electrochemistry. But for our OrChem, its relevant contribution is the discovery of benzene through extraction from our natural resources, okay? So again, Faraday is the first scientist to extract benzene coming from your natural resources, particularly through pyrolysis of heating or of your whale oil, okay? So for Friedrich Wöhler, again, he debunked the vital force theory. So if you're familiar with vitalism or vital force theory, of course, we know that organic chemistry or organic compounds are mainly derived from living organisms, and your inorganic compounds are mostly derived from your non-living substances. So with Wöhler synthesis, he debunked that vitalism or vital force theory because he used an inorganic compound in order to produce an organic molecule, okay? Particularly urea. So aside from that, he also explored isomerism. So this one, he is in tandem with Liebig, okay? Fourthly, we have Frankland. Again, it's about organometallic synthesis. And aside from that, he also introduced the concept of valency, or your existence ng valence electrons in our atoms or our elements, okay? So class, remember, for our fifth chemist, again, we have August Kekulé. You already know, or you are somehow familiar with the Kekulé benzene structure. So that's just simply your benzene consisting a 6-membered carbon ring. And of course, this structural discovery was improved by another chemist through his proposal of your Haeckel's rule, okay? So of course, they are in tandem in terms of developing our aromatic compounds. How do we determine if a certain compound is aromatic or not? Our class, second to the last Cooper, ang main contribution is the tetravalency of carbon. I hope you are familiar that when we say tetravalent coming from your inorganic chemistry, carbon is capable of having 4 valence electrons derived from its electron configuration. And because of this tetravalency, carbons are capable of bonding with at most 4 different functional groups, single bonded 4 functional groups. Alright? So class, again, later we will discuss the specific properties of carbon. But for now, let's discuss the major contribution of Van Hoff, diba? So Jacobus Van Hoff, of course, he's a Nobel Prize awardee due to his discovery of the tetrahedral molecular geometry of your carbon atom. And of course, because of that discovery, it pioneered the exploration of your stereochemistry. I know that some of you found stereochemistry challenging. For this discussion, again, class, we will also cover some of the basics of stereochemistry. Okay, so I hope it's clear. For our next step of your scientists, so these 6 scientists more on development, improvement of our organic chemistry concepts. Again, they serve also as a pillar in order to make organic chemistry more reliable and accurate than ever. Ayan, diba? So class, check your manuals. Here, we have the other 6 chemists. So I will not complicate this discussion. For Gilbert Lewis, he pioneered or he devised your Lewis dot structures. Of course, gamitin yan sa inorganic chemistry. And later you will see that in our structural representation, we also use Lewis structure. So class, he developed Lewis dot structures through the discovery of your covalent bonding and the presence of electron pairs. Clear? Very easy lang yan, class, ha? Next, we have Pauling. So, of course, ang important discovery in terms of the field of organic chem is your orbital hybridization. Now, later, we will discuss this briefly, the hybridization or the different hybridizations of your organic chemical compounds. So, aside from that, of course, this is not relevant. Your favorite part of chemistry, particularly ng phychem, di ba? Quantum chemistry and molecular biology. Again, that's not relevant with our discussion class. So, ang important lang here is the discovery of Pauling on your orbital hybridization. I think you are somehow familiar, di ba, with our hybridization types. sp3 atom, sp2, and sp. And later, we will differentiate their different properties. Okay? So, class, for our next or last four, so this is more of a developmental or improvement of our existing concepts, particularly with Lonsdale. Kathleen Lonsdale used an instrumentation analysis through crystallography experiments. Remember, class, X-ray crystallography is used for structure elucidation, and particularly, she devised the bond length for your carbon-carbon bonds in our cyclic aromatic ring structure of benzene, okay? So remember that. Lonsdale devised our bond length of your benzene aromatic carbon-to-carbon bonds. Alright, for our next chemist, we have Erich Hackel. So class, he developed from his surname, your Hackel rule or the Hackel method. So this one helps us in predicting whether a compound is aromatic or not. So we will discuss the specific Hackel's rule in your aromatic compounds discussion. Class, second to the last, Victor Grignard. Familiar with Grignard reagent. So that's just simply your magnesium metal condensed or bonded with your alkyl substituent with a halogen. Or remember, this is a highly polar compound because metals are electron-poor atoms. Ayan. So class, because of that, much more electronegative ang R group or your organic moiety for your Grignard reagent. And finally, Fischer, we have Emil Fischer. From his surname, he devised, firstly, the esterification method. So this is a typical synthetic route or step in order to produce ester compounds. Later, we will discuss what are the specific features of your ester functional group. And lastly, if you're familiar with Fischer projection, so it's like a fish skeleton or a fish bone. So we use it mainly in visualizing sugar molecules. Please, class, revisit our 13 important chemists that developed the field of organic chemistry. Clear? Ayan. So class, let's proceed with our next discussion. So we are now going to discuss representations of organic compounds, particularly drawing your organic compounds. So class, let's start with our 2D structural representation. So of course, we have several kinds of formulas that we mainly use in order to visualize our organic compounds. Particularly in 2D representations, we have structural formulas. So class, formula defined as, it shows how the various atoms in a molecule are bonded to one another. So recall, for structural formulas, we are concerned with the arrangement of your atoms in a molecule. Also, how about spatial orientation? Class, the spatial orientation is more focused, okay? It is focused on your 3D, the three-dimensional structural representation. For now, let's just focus first on 2D. So we will review first our expanded and condensed type of structural formulas. Firstly, with expanded, this is just similar with your Lewis dot structure. For expanded, you will showcase the bonding pairs of electrons and of course, our bonding between our two different atoms. Consequently, for condensed structural formulas, usually class, our clue word here is the grouping of atoms. Sir, how do we group our atoms? Through the use of parentheses and subscript. Diba? Familiar na kayo with the usage of parentheses and subscript in which central atoms and other atoms, particularly for instance, heteroatoms connected to them, are written as a group. Let's take propane as an example. Check. For expanded structural formula, we are required to show the bonding between your two atoms. So here it is represented by your lines. Okay? Solid lines, particularly for your CH or hydrocarbon bonding. Let's compare it with your condensed. Check. Instead of using lines, we use subscript class. I know you are familiar with our condensed structural formula. This is very important because in the board exam, they will use mainly the condensed structural formula. Here, hindi obvious that we use the lone pairs, but for our next three examples, see, if you have heteroatoms, so what are heteroatoms? Heteroatoms class, those include your oxygen, nitrogen, sulfur, phosphorus, and your halogens. So they are atoms that are not hydrocarbons or not part of your CH bond. Here, I will just emphasize the presence of lone pairs in expanded structural formula. Again, class, Lewis structure or Lewis dot structure lang ang expanded structural formula. For condensed, of course, see, we mainly use your subscript, and if your compound is somehow complex, we will now group it using your parentheses. Sir, question, how about the double and triple bonds? Do we show it in our structural formula? Class, what do you think? Of course, we need to showcase it. So here are the 4 examples that showcase our double bonds and triple bonds. Remember, for both your expanded and condensed, sometimes in your condensed structural formula, we showcase double bonds. But let's remember, sometimes also, we just strictly or straightforwardly give the condensed structural formula, and here, we assume that there is a presence of double bond between your carbon-carbon here, depending on the number of hydrogens. So really, yes, because remember, carbon, class recall from Gen Chem, carbon is a strict follower of octet rule. So its structure is mostly stable if carbon has 8 valence electron in its bonding region. I hope you still remember, sana hindi nag-amnesia ha. Again, for carbons, strict follower ng octet rule. That's why, for condensed, we always assume that if we have enough or not enough amount of hydrogen, there's a presence of double bond or triple bonds. See, for expanded, class required na you show the double and triple bond as well as the lone pairs. For instance, to butene, we have a double bond. Acetonitrile class, we have a triple bond between your carbon and nitrogen. See, we also show the lone pairs present in your nitrogen atom. Thirdly, for acetone, Class, this is a carbonyl group, and check for both of your expanded and condensed, we show your double bonds. Sometimes we did not or we do not show this double bond. So class optional kasi siya with your condensed. For expanded, it is strictly required. For acetic acid, C, again, similar lang, you need to show your double bonds and the lone pairs present. Alright, so class, that's it for our expanded and condensed. But before I forgot, ayan, we still have last 2D representation. And this one, we call this your line angle structural formula. Class, this is the typical structural formula that we use in order to easily visualize your organic compounds, diba? Particularly your alkanes, the saturated, hydrocarbons, and of course, your cyclic structures or cyclic organic compounds. So let's just briefly read first the definition. In your line angle structural formula, a carbon atom is implied at the end of every line and or at every apex or corner, sorry class, ayan, unless another atom, class, usually these are heteroatoms. So here, each carbon atom is assumed to have enough hydrogen to give it a total of 4 bonds in order to strictly follow your octet rule. Again, tetravalent meaning carbon is capable of bonding singly with your 4 different atoms. So let's take cyclohexanol as an example. For condensed structural formula, somehow, it is rather overwhelming. Check the structure. See, medyo overwhelming and messy class if you will also showcase the carbon in your cyclic ring structure, and the hydrogen present in our structure. So most of the time, class, if it's just simply a hydrocarbon chain or hydrocarbon bonding, we will omit directly your C and H atoms. See, sa line angle structural formula, ayan, eliminated ang hydrocarbons, the CH atoms. As you can see at every corner, these are the sides of your carbons, and here we will assume that for your carbons, in order to follow your octet rule, they need to bond with your hydrogen. Class, here oxygen is a heteroatom. Sir, is it required to show your heteroatoms? Yes. And usually if you have a heteroatom, si hydrogen should also be showcased. As you can see for hydroxyl group, remember we have a single bonded or singly bonded hydrogen to your oxygen, so we need to showcase it as well. Class, as a summary, for line angle structure, no need to showcase the hydrocarbon atoms, hydrogen and carbon, but you need to straightforwardly or directly write your O and SPX or the heteroatoms. So let's take other examples here for our discussion. See. For rather complex or for complex compounds, organic compounds in particular, we use line angle structural formula. So I think somehow you also prefer the line angle structural formula. But class, wala tayong exemption here ha. You should also need, okay? You should study also the condensed structural formula counterpart of your line angle structure. So most of the time in the boards, they alternately use your condensed and line angle structural formula. So bihira or relatively limited ang questions that will use your expanded structural formula. See, for our typical hydrocarbons, hexane and hexene, you need to showcase the double bond as well, class. Cyclohexanol, our example from the previous slides, and for benzoic acid. Check aromatic compounds yan. Again, you need to showcase the double bonds, particularly the conjugation of double bonds in the structure of your benzene ring. Okay? So class, don't worry if you are not somehow familiar with the functional groups. We will discuss it as well here in our discussion. But for now, I will just summarize our 3 different 2D representation of organic compounds. Class, as a summary again, we have expanded that will showcase comprehensively the bonding and your lone pairs present in the structure of organic compounds. Again, that's just your lowest dot structure. Secondly, for condensed, we are more concerned here with the grouping. Blue word, grouping of atoms. So we solely rely with your parentheses and your subscript in order to group the atoms. And class, remember, we also somehow optionally showcase the double and triple bonds present in the structure. Lastly, for line angle structural formula, again, it is mainly used for complex organic compound, particularly for your cyclic organic compounds. Okay? So in comparison with your 2D, so let's just have a sneak peek of your 3D structural representation. See. Ayan. So class, firstly, we have the dash wedge line structure. So here, first thing to note is that we have 3 different symbols. Dashes represent bonds receding behind the page. Class, this is your dash component or the dash symbol. Okay? Secondly, the wedges. So this is towards us. It's coming out of the page. So this is the solid bold line or bold symbol in our structure. And lastly, the solid lines. So they are bonds in the plane. So similar with the plane of the page. So usually class, we encounter dash wedge line structure in stereochemistry discussion. So remember, we have 3 symbols. Dash, it recedes behind the page. Wedge, coming out of the page. And lastly, you have your solid lines. Okay? That is similar with the plane of our page. Okay, secondly, we have the ball and stick model. Sir, anong silbi? What is the importance of or purpose of your ball and stick model? Again, that's for the visualization of the exact bond length between your carbon atoms. Okay, so again, it emphasizes the connections or bonds among your atoms, particularly in the tetrahedral arrangement of your singly bonded carbon atoms. Okay, and lastly, space filling model. So this is the most accurate class. So this is how your organic compounds exist realistically. So here, this is the model that emphasizes the overall shape. So very important in class in studying your sterics. Okay, the steric strain or the hindrance, particularly for bulky molecules. Okay, let's summarize the 3D representations. Again, dash wedge line structure for stereochemistry discussion studies. Stick model, particularly to showcase the bond length of your organic compounds, and lastly, space filling model for the sterics. All right, most accurate again to space filling model. All right, so that's it for our discussion on your representations, structural representations of your organic compounds. At last, breathe muna, hinga. I know for organic chemistry, comparing it to your other subjects, this is more of a theory-based subject, so more on concepts tayo class. So if there are computations, very minimal lang. So for now, you can pause the video, you can take your CR breaks or snack break, but for me, I will continuously discuss our next topic class, the intro to your organic chemistry, okay? Ayan. So here, I will discuss our core theory that gave birth to your organic chemistry. So class, remember, currently, when we say organic chemistry, this is primarily the study of carbon-containing compounds. But historically different ang definition ng ORChem. So that's based on your vitalism theory. Remember, I discussed it earlier sa history ng ORChem. In vitalism or vital force theory, we believe that somehow organic compounds are derived heavily or primarily from living organisms. They are strictly derived from living organisms. But you know, it was debunked by Friedrich Waller through the synthesis of urea coming from ammonium cyanate. Class, for inorganics, based on your vitalism, they are derived daw sa non-living substances. And class, in our age today, that's clearly false. Okay? So here, we define ORChem as carbon-containing compounds, and in organic chemistry, the rest that do not contain carbon. Okay? While nearly all compounds found in living organisms are considered organic, emphasis in here, many compounds, synthesized in the lab that have never been part of a living organism are also classified as organic. Our class, check here our pie chart. As you can see, organic compounds somehow, it is relatively high in percentage. So 10 million of your compounds or chemicals exist as organics. So only a part is considered inorganic. See, again, because of the chemical reactivity of carbon, it can give rise to different structures. Sa allotropes pa lang ng carbon, you see, we have numerous novel or unique chemical compounds. Class, I hope it's clear. Again, for organic chemistry, this usually focuses on compounds that contain carbon. Alright, for inorg, ayan, the rest. The other 117 elements. And remember class, you will frequently see these three main characters in ORChem. Again, we have three main character elements here. Ayan, if you have watched Harry Potter, diba? We have here the cast of Harry Potter. Here we have oxygen, carbon, and hydrogen. And remember, they are always part of your organic chemistry discussion. Okay, so class, remember, again, organic chemistry, that's just simply your carbon chemistry or your carbon-containing compound chemistry. And remember from our discussion in your intro to organic chemistry, carbons runs the chemistry world. Ayan, so here is our did you know segment here. For carbons, again, currently, on current count, we have 90 million organic compounds. And almost all of them are considered organic. Carbon ang base ng structure niya. So remember class, ang reason behind this, that we are able to give rise to different carbon-containing compounds relies on the chemical reactivity of carbon. And that's why we also need to discuss the properties of carbon. Or recall, here we have examples of carbon compounds. Firstly, through combustion, we produce mainly carbon dioxide. Okay, so we will discuss this, don't worry, on our alkanes discussion. So as our genetic imprint, I hope you are familiar, we have DNA. Okay, for methane, of course, primary component yan class ng natural gas. See, may sneak peek na tayo for our fourth example. This is benzene, a type of aromatic compounds. And lastly, what is this functional group? Check the structure. It has a hydroxyl. Sir, ethanol is an alcohol functional group. Yes. So class, again, we have over 90 million organic compounds. And that's because of the properties of carbon. Remember, we will discuss here three most important properties ng carbon. Somehow we discussed the first one, the tetravalent nature of carbon. Okay? Ayan, let's continue and transition to our last topic for our first set of discussion in Intro to Organic Chemistry. Our class, first property, again, carbon is tetravalent. So it just simply means that, again, it can form 4 bonds with itself and other elements, usually heteroatoms or ONS-PX atoms. Okay? So again, class, I will repeatedly emphasize this. Carbon is a strict follower of octet rule. So gets na namin yan. What's the next property po? Class, this one is the ability of carbon to form single, double, and triple bonds within itself. Okay? So again, primarily within itself and with your heteroatoms, particularly with your oxygen and nitrogen atoms. Diba? Additionally, carbon atoms can also bond with one another to create linear, branched, or cyclic chain or cyclic compounds. Class, this specific property, we call this, I think you're familiar. I hope you are familiar pala. So again, we call this the catenation property of carbon. So again, that's the ability of carbon to form linear, branch, or cyclic chains through covalent bonding within itself. Okay? So class, this is the typical bonding mechanism of carbon. Again, strict follower ng octet rule. So realistically, it can carry 8 valence electron in its bonding region. Starting with your first type, again, single bonds. So maximum of 4 single bonds in order to have 8 valence electrons. Class, recall lang ha. Per line here, this consists of how many valence electrons? Diba? We have 2 here. Check. If we have 2 per lines, of course, for 4 single bonds, we have 8 valence electrons. Clear? Next, another type is the presence of 1 double bond and 2 single bonds. Double check class. If we have really here 8 valence electrons. For double bonds again per line or per single line, it constitutes of 2 electrons or 2 valence electrons in particular. Sir, I know 8 valence electrons yan. Yes. For double bond we have 4. Single bonds again, 2 each single bond. So total of 8 valence electrons. Thirdly, if we have 2 double bonds, check. Again, this constitutes of 8 valence electrons. Another type of bonding, if we have 1 triple bond, again, class automatic, your carbon is only capable of having 1 triple bond and 1 single bond simultaneously. Okay, maximum of 4 single lines lang class. That's my general tip. Okay, so lastly for cyclic, ayan. So usually, again, we use the line angle structural formula in visualizing our cyclic structure. Clear with our first 3 properties, tetravalency, ability to form single, double, triple. Okay, and lastly, the catenation property, ability of carbon to form linear, branched, and cyclic structure. Okay, so last. Ayan. Lastly, class, your organic molecules can exhibit both structural and stereoisomerism. So for our discussion here, let's just focus first on your structural or constitutional isomerism. Sir, are these similar terms? Yes. Okay, here, for structural or constitutional isomers, class, read the slides. Our keyword here, same ang molecular formula, but their stark difference is in their structural arrangements. So usually, class, ang constitutionality or the constitutional isomers here in your organic compounds are done through branching. Okay? So of course, if we do branching somehow, magkakaroon na yan ng different physical properties of compounds. O sir, pwedeng example para clear yung discussion. O let's take pentane as an example. Or recall, class, how many carbons do we have in the chain of your pentane? Even though wala pa tayo sa nomenclature, so I hope you are familiar for pentane. We have 5 carbon saturated organic compound. Let's check. For pentane, we have 2 distinct structural or constitutional isomers. Again, due to their different type of branching, we have isopentane and neopentane. Class, in this slide, I will emphasize the effect of structural or constitutional isomers with your physical properties ng organic compound. So again, pentane, linear structure. Here in our discussion, we will go back again with your inorganic chemistry concepts. Recall, if you have a large surface area for your organic compounds, we have larger sites for IMFA. Sorry, class. IMFA, that's your intermolecular forces of attraction. O sir, ba't po pag nag-increase ang surface area, increase din ang IMFA? Because exposed class ang carbon chain natin for our IMFA. Okay? See, for the boiling point of pentane, we have 36 degrees Celsius. Sir, how about branched pentane? What will happen if we have branching in its structure? For instance, we have isopentane, the branched counterpart of your pentane molecule. See, we have a methyl substituent at the C2 position. Class, again, common name to later we will discuss the nomenclature based on the IUPAC, and of course, we will also somehow touch on the common names of your organic compounds. Going back, check. If you have branching class ang trend dyan, it will lower the surface area. And as a result, if you lower the surface area, see, IMFA will also decrease. Sure, what's the reason? Because we have few, okay? We have few available atoms for IMFA, particularly for London dispersion forces. Class, please revisit your inorganic and Gen Chem discussions. Check what is the effect of the branching or decreasing the surface area. See, the boiling point also decreased. So generally, or in summary, they have direct relationship. Let's see our last example, neopentane class. That's the highly or the most branched type of your pentane constitutional isomer. See, we have a quaternary carbon. Class, as a background, when we say quaternary, ang single carbon is bonded to 4 different carbons in its structure. Okay, here, your neopentane, check the boiling point. Highly branched meaning relatively ang surface area niya is very low na or decreased na class. So yung IMFA in its structure is very low na rin. That's why ang boiling point check, we have only 10 degrees Celsius. Okay, so class, that's it for your properties of carbon. Let's have a recall again. First, property, tetravalency. Second, ability to form single, double, and triple bonds. And lastly, we have your catenation, ability of carbon to form linear, branched, and cyclic structure. Ayan. Class, diba? Napaka-main character energy ni carbon. And of course, in organic chemistry, very evident. See the meme? Ang superiority complex ni carbon. Remember, because of its properties, it also affects the properties or chemical properties, particularly the chemical reactivity of your carbon compounds. Alright? So class, that's it for our first set of topic. So if you need or if you wanted, for curiosity lang class, if you wanted to visit or study more of your 3D representations, you can visit vcam3d.univ. Okay? So this one, it simulates our typical organic compounds. Ayan. So class, that's it for our first topic on intro to organic chemistry. So for our next topic, we will discuss naming of your organic compound. Alright, so class, we will continue our discussion here for your Crash Course 1 in our next video. So recall, we are already done with the intro and the properties of carbon. So for our next video, we are going to start with our discussion on your nomenclature. My class, see you in our part 2 of Crash Course 1. For our next topic, we have your naming or nomenclature of organic compounds. So under our topic here, we have your subtopics. Remember, our nomenclature is based on your IUPAC system. So that's why we also need to focus our discussion on our nomenclature systematic way of naming. Second, we will also discuss your functional groups and compound classes. So class, remember, these groupings are based on the chemical reactivity of our